Hello. Today, for our second episode, we are going to be learning about how to selectively overcount. So it turns out in some cases, it's often much easier to count a number of cases where you omit one of the parameters and then thereby put that parameter in later, subtract the number of cases where that parameter doesn't meet. So it's often easier to subtract, to find a overcounted value and then subtract from it. So, ordering distinct and non-distinct objects. So we've already tackled the way of ordering just a sequence. So A, B, C, D, E. We know the number of ways to arrange this is 5 factorial. Now, what if we had the arrangement ball, and we assume that the two L's are non-differentiable? When you switch these two L's, it does not matter. The arrangement is the same. How do we know the number of ways then? Well, instead of simply trying to count all the ways inefficiently, we could still proceed about as if these two L's were still differentiable, like so. So we could mark them with like L1, L2. How many ways are there to order them now? Well, because they're differentiable, immediately it's just like the above sequence. It's 4 factorial. Simple. But now we need to correct for the cases where the L's are swapped. In this 4 factorial, it counts the L's swapped as different arrangements, and we have to get rid of that. So how do we do that? Again, we need to simply find a number of cases where L is swapped here. So, in order to find those cases, we can simply find a number of arrangements where the number of ways these L's can be swapped. And because we take these L's like another mini sequence of letters, we know that there's 2 factorial, or just 2 factorial. There's just 2 ways to arrange these L's. So we know that there is, for every arrangement for these total, there's 2 factorial kind of multiples of them that have these 2 L's swapped and counted as different. So in order to get rid of that multiple, we just divide by 2 factorial, which equals 12 arrangements. Again, don't try to memorize this formula. Understand why it works. We are dividing by the number of cases where the L's are swapped. 2 factorial is simply the number of ways L's can be arranged and swapped. Alright, so now we move on to a more complex example. What about balloon? Now again, as before, we cannot have these two the same. Like, we cannot swap these. So again, just like before, we assume that these at first are different. Whoops. We assume that they are different. So again, now we know how to proceed. There's 8 factorial of these. Now we need to again find the number of ways. We know that the number of ways to arrange the L's and the O's, both of them are 2 factorial and 2 factorial. Note why you cannot assume that these can just be 4 factorial. It's because the L and the O are not mutually exchangeable, like they're mutually differentiable. You cannot swap the L and the O and count them as the same. So it's not 4 factorial, it's 2 factorial and another 2 factorial. So just like before, 8 factorial divided by 2 factorial for the number of L's, and then O factorial for the number of O's. in which they are swapped. Now, for our second problem, let's talk about symmetry in a geometry kind of way. So, for our first problem, we have 4 people sitting around a table. How many ways are there to order these 4 people if they are all different? Again, we could letter them like so in order to make them different. However, any arrangement in which these are simply rotated is counted as exactly the same. Rotating them around is not going to, it's going to be the same. Just like if you're on an actual circular table, this entire thing can be rotated, and then it's the exact same arrangement. So how many ways are there to do that? Well, again, as we know, simply ordering them is 4 factorial. 4 people, there's 4 ways to order them. However, there's also 4 ways to rotate them. So, in order to correct for this rotation, every time you rotate it, it counts as an extra. It counts as a different arrangement, and that's not allowed. So, in order to correct for this overcounting, we need to divide by 4. The 4 total rotations for every, remember, for every arrangement of ABCD, there are 4 ways to rotate them and make them different. So we need to get rid of those 4 ways by simply dividing. So it's 4 factorial over 4, which equals 6. Now, on to a slightly harder problem, or just harder problem. What if we had 10 people around in a circle, and 2 of them had to be directly opposite each other? How many ways are there to arrange this? And of course, assume that they're all different. How many ways are there to do this? So, we could first, again, approach by overcounting. There are we already know, 10 factorial ways to have an arrangement of all of these 10 people. But, again, as we said before, symmetry. So we need to eliminate 10 of those rotations. So there's 9 factorial. We have 9 factorial now. And if we think about it, we could think about, for example, A over here as a kind of fixed person. One way to think about it is A is a fixed person. Whoever is opposite A, let's name him B, is already fixed. There's no way that it can be anything but B. So what we need to do is just simply fill in each of these people. So, in order to do that, we could think about it as kind of just an normal 8 factorial. Again, try not to make the mistake that I did when I first encountered this problem. Don't do 4 factorial times 4 factorial. These 2 sides, while they look, separated, they are still mutually exchangeable. You can switch them freely. So instead of 4 factorial, it's 8 factorial. So we have a total of 8 factorial for these. And then we have a total of simply 8 factorial. But, again, don't make the same mistake that I did. Alright? A and B can switch. And this is a very, very different sequence. You cannot rotate this to get the same position as if A had never switched with B. So, at the end, the total number is 8 factorial times 2. Now, for the final challenge problem. Based on the other 2 problems that are like this, I'm going to give you a moment to think about this and pause the video if you need to. What if, instead of just one, there are two pairs of people that have to be directly opposite each other in 10 people? What then? Well, we could again begin by approaching that noting A and B can be fixed. However, in relative to this, because A and B are fixed, this basically already accounts for our overcounting symmetry. Because A and B are fixed, rotation is exactly the same. Now, this, let's call him C and D. Let's say D is fixed relative to C. And C can have four positions. C can be in this spot he already is in here, here, or here. So, total right now we have 4 ways for C if A and B are fixed, multiplied by 2 ways for C and D to switch, and 2 ways for A and B to switch. Now, then we have these people. Again, there's an easy way, 6 factorial ways to arrange them. So, let's do a little check. We have 4 ways for C and D times 2 ways for C when C and D switch. Notice that unlike if there was an odd number here, when you do flip A and B and C and D, there is no physical way for them to be rotationally symmetrical. Times another 2 for C and D times a 6 factorial for the remaining people. And that's it. See you next time.